Okay, all right. Okay, great. So welcome back, everyone. So next we have Rob Smith from our team software, and he's going to speak to us about WebVMT. So without delay, Rob, over to you.
Thanks, Gavin. So, my name's Rob Smith from the WAVE team. I'm an invited expert in the spatial temporal data on the web group, which is a joint committee between OGC and W3C. At OGC, I'm involved with geoposing moving features, and at W3C, I'm leading development of Web Video Map Track, WebVMT, designed to synchronize location with video for the web. I'm also involved in the YCG data queue HTML element for timed video metadata in web browsers. And I'd like to talk to you today about video metadata, including GIMI, to explain what this can do and why that is important, and explore some of the community tools that are available as well, which help to extract metadata in a more accessible form, and show how this can help to quickly find relevant video content, and then tie all of this together with a demo, which is a dashcam collision monitoring use case that I was looking at in OGC testbed 21, that identifies events of interest from metadata associated with video and location using a web application in a web browser. So let's get started. Video metadata, what is it? And how can we integrate this with GIMI? The image here is a maritime use case that I looked at in testbed 20. If you want to find out more about that, have a look on OGC's YouTube channel. There's a video about it, quite short. But let's start with the basics. A video file, or more generally, a media file, can contain three types of content. So there's a video stream, which is a sequence of still images or video frames, an audio stream, which is a sound recording chopped into short segments, and a metadata stream, which is other data, things that aren't video or audio. Hopefully this isn't too much of a surprise to you. But what we think of as a video file actually contains a video stream and an audio stream. It's a feature film or a TV show. And the sound and image recordings are fundamentally different. So image is recorded with a camera, sound is recorded with a microphone. So all video streams are silent because the sound is recorded in the audio stream, and we need to synchronize those two together. And that's the purpose of the media file, though it's not immediately obvious because we're so familiar with these things. The clapperboard, which you see at the top of the media file there, is iconic in the film industry. But does anybody actually know what it does? Anybody in the room? No. Okay. Why it has that hinged arm at the top? It produces an event that can be heard and seen, and that allows the picture to be synchronized with the sound. When the arm closes, it makes a click, and that allows the two streams to be synchronized. So it's actually the predecessor to the media file and to WebVMT as well. Media files can also contain multiple streams. So something like a CCTV system monitors an area with multiple cameras at different locations. That's multiple video streams. Or an autonomous vehicle has cameras looking in all different directions. Ordnance Survey street drone vehicle, for instance, has 8 cameras on it. And there are also use cases for multiple audio streams. So dubbed films have multiple soundtracks. You select the audio stream you want in the language that you want. So you'll notice so far I've only talked about video and audio, but the same rules apply to metadata. So we can synchronize data streams with audio and video, and a metadata stream can contain literally anything. So in geospatial terms, that can be location, speed, heading, or sensor data. So for a dash cam, that might include an accelerometer. It can also have derived data, so data derived from the audio or video, so we can tag these things. for instance, an animal type that's visible in a wildlife camera, a particular species, or a car number plate that's seen by a roadside camera, or more mundanely, tree branches that rattle against a bus roof, which indicate that the trees need pruning at this particular location and might otherwise damage the vehicles that are passing by. And they can provide an intermediate step in a process as well. They identify an event of interest which relates to either a single video frame or a video clip. That is a way to provide quick access to the relevant content. The media file also has its own timeline, which makes it easy to access. You can see that at the bottom of the media file here. It's a simple increasing count in seconds. There's no confusion with different calendars or leap seconds. For instance, GPS time has an 18-second offset from GMT or UTC. Catches a lot of people out. And we can optionally tie this to a time and date for comparison with other data. So how can we access metadata? This can be tricky. Consumer markets are dominated by proprietary formats, and the metadata can be embedded within the video file, which is in-band, or it can be recorded in a separate file, which is out-of-band in a sidecar file. Fortunately, there are some community tools available. So this is a tutorial. So here's a short list of some to get you started with. This is not exhaustive by any stretch of the imagination, but some of these are not intuitive. The EXIF tool, for instance, is for supposedly extracting EXIF tags, but it allows us to access and manipulate metadata embedded within a video file. It's actually got quite a good compatibility with a lot of different video formats. And specifically, it has a feature which, or combination of features that allow it to export embedded location data into GPX format in a single command, which is very useful. Next up, we've got FFmpeg. This also includes FFplay and FFprobe, which are for file playback and analysis. So that's quite a useful tool. libHeaf. This includes an encoder and a decoder, -enc, -dec, for encoding and decoding heap files, still images, and image sequences, which is the basis for GIMI, and also MP4, so full motion video. And finally, GStreamer, which includes a couple of tools called GST Launch 1.0 and GST Inspect 1.0. Not very snappy names, but they allow us to run stream pipelines. I'm not going to go into all the details of this because that's way beyond the scope of this talk, but links are provided here so you can explore these for yourself and experiment. And these tools provide ways to identify and extract metadata from a range of video formats. So let's look at some examples. Encoding video metadata into GIMI. We're talking about GIMI today. So a new feature was developed in OGC testbed 21 to add a metadata track to a GIMI video file from a VMT file. And this is a two-stage process. So you can extract video frames from a video file using FFmpeg with the command shown here, and then we can encode a metadata track into the video file using heaf-enc from libHeaf. And the metadata is read from a VMT file using sync commands, which supports binary formats such as MISB metadata and GPMF, GoPro's format, and text formats, things like JSON, XML, RDF. So that means it also covers GIMI's IDO, the imagery domain ontology. So on the web, MP4 video is well supported in web browsers. So GIMI video is immediately compatible. However, embedded video metadata is not supported. in web browsers. And that is what WebVMT does. Provides a mechanism for accessing video metadata on the web. So the same VMT file, which can encode the metadata into a GIMI file, can also display that metadata in a web page, as you can see here, the green text at the bottom. So let's explore some common use cases. Tracking a camera location and accessing binary metadata. So a common use case is to have a camera that's on the move, a dash cam or a body camera, and we want to track its location for the duration of the video. And as I've already mentioned, EXIF tool can export the location data embedded in a video file to a GPX file. We're then able to convert the GPX file to a VMT file at the webvmt.org website. Just drop your file into the GPX importer community tool. There's no upload, it's quick, respects your privacy. It's all done in your browser. And you notice that the system also works for any system that can export a GPX format. So for fitness apps, things like that. Now we have two files and we can display the video with a synchronized map in your browser, again, just by dropping the video in the VMT file into the mobile demo on the WebVMT site. Again, it's done in your browser, no upload or anything like that. Quick and simple, respects your privacy. Or you can build and publish your own web page and share your metadata on the web. So secondly, accessing binary metadata. We can export the data to WebVMT sync commands and access binary metadata like MISB in a web app. The VMT file is text-based, so the binary needs to be encoded, but we've got a couple of options here. So firstly, there's hex encoding, which is easy to read and edit for humans, but it does double the data size. Alternatively, we've got base64, which is more efficient, pretty illegible to humans, but machines don't have a problem with it. And it's the same technology that's used for email, which is also a text-based format, but you can send binary files by email. I'm sure everybody's familiar with that. Maybe you haven't thought that there's text going on underneath here. The web app that receives these is agnostic of the encoding. It just sees the binary array, so it all just melts away. And if you want to find out more details, have a look in the community group, issue number 15. There's a link here. Web app then can listen for synchronized queue events. Content is handled as a data queue, HTML data queue, or a custom queue, and we can filter queues by type. So we only look at the queues of interest. There may be other things mixed in there, but we don't waste time looking at those. And the metadata content is read as a binary array. And there are several ways to implement this. It's all about choice. So, as I mentioned, we can. There's an option to use custom queues instead of data queue. Data queue is a very simple type and value, so it's good for raw data, things like MISB binary. A custom queue allows us to create tailored functions, allows developers to create tailored functions. So for MISB, for example, you could implement functions such as get sensor location, get target location, but this is all an implementation decision for the developer. Depends how readable you want your code to be. And there are several other choices available, such as whether to stream different queue types in a single metadata track or have each queue type in a separate metadata track. Some options work well for particular use cases. This might seem a bit of a huge choice, bewildering. So there is a VMT sync examples repo which explores these implementation options with working examples. So the net effect in the page may look the same, but under the surface, it's working in a different way. And developers should know how to open the console log in their browser, and they will be able to see the difference, how these different examples are working. There's about a dozen of them, I think, now. And this repo also provides guidance for developers to select their best option, say what these things are well suited to. It also explains the key differences between WebVMT and WebVTT, which is for time text with subtitles, which has a totally different set of requirements, though time text is really just a very specialized form of time metadata. So let's look at a use case. This shows how technologies can combine to enrich video with metadata. It's a dashcam collision monitoring use case, which was filmed with a next-based dashcam system, which you can see here, which has a front and rear camera. Those are in my car. And it produces 2 video streams with audio, and also a metadata stream, which includes location, speed, and 3-axis accelerometer data. And the aim is to identify collisions from spikes in the accelerometer data, the timed metadata, so we can quickly find relevant video with location and speed for events of interest. And it provides admissible evidence for insurance claims and police investigations. So it has commercial value to protect employees and company vehicles. The data were recorded at Ordnance Service headquarters near Southampton. I didn't crash my car, but identified another commercial use case, which is pothole detection for road network maintenance using a fleet of dashcam equipped vehicles. So a vehicle collision is a horizontal impact, and a pothole is a vertical impact because you drop into the pothole. And that means that we can see the difference in the metadata and differentiate between these two. So we exported the binary metadata to a VMT file. The dashcam produces a proprietary format at 10 Hertz, so these are every 100 milliseconds. But we just treated this as a black box because at this stage, we're not really interested in the content. How do I move that window? I don't know, that? Yes, that's better. Now you can see the picture. Sorry about that. So we synchronized the binary data with video in a parameter, as you can see here, and accessed this as queue events with HTML data queue in a binary array. And then analyzed the binary data to determine the content structure. And there are 2 NMEA sentences in there. Anybody familiar with those can probably see those in the text, but they start GPRMC and GPGGA a little further down. So those are 2 location streams coming through, and there's also accelerometer data in there, 3-axis. So having worked out the structure of this, we were able to identify timing anomalies, which affected more than 10% of the data, which is significant. There's duplicated data, missing data that has misaligned timing. So some software is required to correct all of that. We were able to correct the misalignments to improve the data quality, separated out those 3 streams, the 2 location and the accelerometer, into 3 JSON streams in a VMT file, corrected the timing issues, handled the missing data on a per stream basis, and reduced the damage to about 5%. So roughly a 50% improvement. A web application was developed to filter and explore the data. There are 2 renderers at work here. So firstly, we've got the WebVMT engine in blue for the purposes of this demo. You can see the track there. And the web app is rendering in orange. And there's a video toolbar at the top, which allows us to toggle between front and rear camera and shows a video time in milliseconds, because we only have 1 second granularity in the standard browser UI, and we need more detail than that. And at the bottom, you can see a metadata toolbar. This has an accelerometer toggle to hide the orange data, so we can see the map behind. and there are controls to filter the accelerometer data, to select an axis, range or threshold, and then a slider to adjust the value, and a hold toggle, which freezes the accelerometer data display, the orange data, so we can see data in the future, because remember, this is all synchronized with video. And I can demonstrate all of this right now, assuming the technology doesn't fall apart at this point. So, how big can we go today? That's quite nice and large. So, this is binary demo, which isn't working. Brilliant. Why is that not working? Reload. And there we go. There is a video. I can't see the controls. So hang on, let's go back. You can see there's a traffic island here, and if I flip around, I can see that in the rear view. Now I can't, because I can't press that button for some reason. Trust me, you can flip around and see this in the rear view. Apologies for that. Don't know what's going on. But you can see that the metadata at the bottom, we've got in the top line of the bottom panel, we've got a metadata timestamp and the video time. They're advancing in steps larger than 100 milliseconds. That's just because the display is updating slower than that. But if I pause, I could jump around here, and you can see that these two times are within 100 milliseconds at all times. So if I go to next demo, this is the same video. There's some peculiarities with the display going on here. Let me see if I can set this one away. Yes, good. All working. Same video, but now we've got a map at the bottom. So you can see a blue track at the bottom of the screen, bottom of the lower panel, with orange highlights from the accelerometer data. And the filter is currently on the lateral axis below the threshold. So it's only highlighting left-hand turns. So you can see a left-hand turn, the right-hand turn is clear, but I can change that in real time, set it above, move the threshold up. I'll do it slowly so you can see it change. And now we're only highlighting right-hand turns. And you notice that the video's running throughout, so this demonstrates the support for stream data. And it also works while it's paused. So if I just pause, I can change to the vertical axis here. And outside, so we're looking at accelerometer spikes, everything away from the center. And this detects vertical impacts. And it immediately shows us that we've got 3 locations highlighted. So if I zoom in on these, wait a minute, to hold that data and zoom in like so, you can see that there is a speed bump here marked with 4 white triangles. If I click on the first orange spike, that synchronizes the video to that particular frame. You can see that the video time matches the time on that circle. And if I toggle off the accelerometer data, you've got a very clear view of the speed bump there. But if I click on the second spike, well, the speed bump's now behind us. If this button now works, oh, good. That's a relief. I can now see the speed bump behind us in the video display at the top. And if I zoom out, we can check the other locations. So second speed bump, there it is, and the same for the third. So we're quickly able to identify relevant video content just from the metadata here. So if I just stop sharing that and go back to the presentation. So we've been able to analyze the dashcam collision monitoring use case with web application. This has given us access to timed video metadata in a web browser that handles text and binary metadata formats, synchronized with video using WebVMT and data queue, agnostic of video encoding, so it's interoperable with GIMI and with other formats. It's integrated with HTML and CSS to leverage web technologies, and we've implemented interactive controls built on top of WebVMT. And detailed results of this will be published in the forthcoming Testbed 21 report you see here. And finally, we have shown how to have timed metadata integrates with video, how community tools can extract video metadata, how to encode metadata in a GIMI video file, how to share and access metadata in a web browser, including GIMI, how to develop a web app that utilizes video metadata, and where to find help and resources online. So I'd be interested to know what you decide to build. I'm always interested in new use cases, so please let me know. Thanks for your time. Happy to take any questions.
Okay, thanks, Rob. Okay, are there any questions or comments for Rob? Anyone online have a question? Okay, so I've got I suppose it's both a question and a comment. So there's one use case that that keeps coming up, at least. So there's I think we called it the letter detection use case, like so basically being able to identify letter perhaps along a road or perhaps even on the road from VMT based video, and I thought, well, maybe that's also should I say an opportunity for something along the lines of change detection, because in some environments, you know, in some environments, like in conflict areas, for instance, if if there's something along a road that you don't really expect it to be there, like, you know,
an obstacle.
Yeah, an obstacle or just anything that you might not expect to be there, because it could be, you know, it could be a threat or something like that, right? So or some form of hazard. You potentially could use something like this to be able to, you know, to compare video from previous journeys along that path, and perhaps do some automatic change detection or something like, or anomaly detection or something like that.
Yes, absolutely. So I think there are two use cases there.
Yeah.
For moving the static cameras. So if you have roadside cameras,
Yeah.
this is a common use case to detect an obstruction in a particular lane.
Yeah.
The camera has a fixed view, so it's very easy to work out what it sees in general, different lighting conditions and so forth, which can be a challenge.
Yeah.
But if there's a foreign object in a particular lane, then you would like that to flag quickly and automatically to say there's a problem here.
Yeah.
For the dashcam use case, which is I think the one you're describing.
Yeah.
Again, yes, you could. This is the pothole detection use case. So you have a fleet of dash cams, maintenance fleet that goes out on the roads anyway, or delivering public transport. There are a lot of vehicles that routinely travel. Stick a dash cam on those, and then compare that data over time to say, this is what we saw last time.
Yeah.
Are we seeing a problem? And so if there is an obstruction, when you have to tell the difference between some static object and another vehicle, because there's other vehicles on the road all the time.
Right. Yeah,
so that's going to be a bit confusing.
Well, it's something for AI to do, right? Because it can
or
easily,
some
yeah,
systematic process.
yeah,
I think there's always a better way than using AI. Um,
true, true.
but I take your point. Some
Yeah.
processing.
Uh,
So yes, if we can identify a static object and
mm,
then go back, flag it to an operator to say, I think this might be a problem.
yeah,
And then go back to previous passes of that same location. Yeah, that's exactly what we're talking about here. Access previous video by location.
yeah,
Tell me what this looked like yesterday or the day before, the last time the vehicle came along here,
yeah.
and when it changed.
Is there an annotation thing in WebVMT? Like, are you able to say at this point in time there were such events or these detections were made, or is there like a way to annotate a particular point in time in a timeline or time series?
Yes, not. Yes and no, I think is the answer to your question. WebVMT does one thing, which is synchronize. It synchronizes whatever information you want to synchronize with video.
Okay.
So it's the universal solution.
Okay.
What you put in there
It's up to you.
Is up to you.
Okay.
But you can. The important thing is you can label it. So here, this is why data queue is of the form that it is. I go back to that. It has a type and value. So the type is a label. So in this example, MISB, and the value is whatever data you want in whatever form you want. It could be binary, it could be JSON, XML, RDF, whatever. So yes, you could come up with an XML or JSON schema to put your data in there. You can say when it starts and stops, when it's visible, or you can just say when it starts and have it stream. So the next one will overtake it. So there's two ways to do it. So absolutely is the answer to your question. Some thought is required.
Okay, cool. Are there any other questions or comments from anyone either in the room or online?
Very unrelated question to WebVMT. I remember last time you guys had a big challenge with obfuscation and removing this type of data from images. Is that resolved with an automated work since last year, or still a challenge?
It's an ongoing problem. Steve came up with a solution. I wasn't really involved in that, but so the problem was we recorded in the same location at Ordnance Survey. So there were vehicles driving up and down the road, and you can see the number plate because we have roadside cameras, just smartphone on a tripod. So inevitably they would come close enough to read the number plate. Okay, we're not trying to doxing people. So we needed to remove that because we wanted to publish the data, the raw data. And there's also a footpath. So people walking past and sort of looking into the camera or looking away from the camera, depending on their personality. So we wanted to obscure the faces. But Steve came up with a scheme to do that, which I think used AI.
Because I know with FFmpeg you can mask a section of the video clip, like of the frames, but you then need some other logic to move the masking with whatever it is that is.
And we had the problem that things were far away and then came close. And that's quite a different issue. And moving around in the frame, there's a person in the distance, and then they come right into sort of the whole frame. Scale was a problem. But yes, he came up with a solution to that. So that's the Hillyfield's bubble data set you're talking about, which was published. That's open data. So people can go and play with that. Let me know if there's anybody online who wants to go and explore that. Please get in touch.
Okay, I think that's it. So let's thank Rob again for an excellent presentation and discussion, please. Okay, so there's two more lightning talks after lunch. The first one at 1:30 and the second one at 2:30 London time. So see you then.